Good afternoon, all of you. My name is Nitin Tomar. In today's class, we are going to discuss some problems from the numerical analysis. Before that, we are going to discuss some basic fundamentals of limits and continuity in terms of purely mathematical sense, that is, in the sense of epsilon delta. So we start with some definition, or let us say with some points to be revised which we shall need further. So given a sequence an of real numbers where this n varies over natural number, we say that limit an exists and is equal to L if for every epsilon greater than 0 there exists a natural number say n naught, such that the following things holds: mod of n minus modulus of an minus L is less than epsilon for every n greater than equal to n naught. So this is what we mean by a convergence of sequence. Convergence of sequence of a sequence and the similar epsilon definition we use to define the continuity of a function. So here what we are doing, we are revising some fundamentals in mathematics which you must have seen in your real analysis course, and numerical analysis in itself is the applicability of real analysis in practical life problem. For example, in coding, machine computations, this theory is very much useful. So let us define a continuous function. Continuous function just a minute, I will continuous function. So here the functions that we are considering are real valued. So let A be a subset of R and f is a function defined on a and is real valued, which means the values of f are in the real number. That is, the image set of f is a subset of real number, and c belongs to a, and we say that f is continuous at c f is continuous at c if given any number epsilon, any epsilon greater than 0, there exists delta greater than 0 such that if x is any point of a, x is any point of a satisfying mod of x minus c less than delta, then we must have modulus of fx minus f of c to be less than epsilon. Now, so this is the definition of the continuity. Again, this you must have seen in your real analysis course. The aim here is to revise the definition of the basic definition that we might need in future to learn the fundamentals in the numerical analysis course. So because today is the first tutorial, a major part of this will be invested in revising some basic definitions. Note that if f fails to be continuous at c, then we say that f is discontinuous at c. So this is the definition of continuity at a point. So this is my first point. Second point being if f is continuous at every point of a, we say that f is continuous on a. We say that f is continuous on a. Now what we shall see some results that will be highly useful in this course, which are applications of a continuous function. So we shall see that some preliminaries and results. So this one is very important and is known as location of root theorem. Location of roots. Okay. Hello Pranjali. Am I audible?
Yes.
Okay. So right now what we have covered is the definition of convergence of a sequence and the definition of continuity at a point. So if you have any doubt in that, please ask. Do you know the epsilon definition of limit? Okay. So now we are up onto this location of roots theorem. So what does it say? One thing I would like to say, if you have any doubt, however trivial it may seem, please ask. Stop me and ask. My language for conversation is English and Hindi. So I'll continue with the theorem. So let I to be this interval AB and f be a continuous real valued function on this interval. Now if f of a is less than 0 is less than f of b, or okay, let us write in the this very useful information in the next line. If f of a is less than f of b, or f of b is negative and f of a is strictly positive, see, we can write this two equation in one line by saying f of a times f of b is strictly negative. Okay, we can write it like this. Then what happens? Then there is a number c in between a comma b such that f of c is 0. Okay, so we will not go into the proof, but as an example I would like to share one function on which we will apply this theorem. So example, consider this function fx xe minus x, sorry, xex minus 2 equal to, yeah, minus 2. Now let us say our aim is to find the Our aim is to find an interval in which this function has a 0. So let us write our aim. Our aim is to find a 0 of f of x. See, most of the time what happens, solving a functional equation is not easy. For example, even if you have, okay, to begin with, we know how to find zeros of a polynomial up to a certain degree. For example, if it is a linear polynomial, we know if, and if it is a quadratic polynomial, that is a polynomial of degree 2, then we have the quadratic formula. As we keep on moving to the higher degrees, for example, if I have a polynomial of degree 3 or 4 or 5, we will see that finding a 0 is going to be really difficult in further cases. So how to find a 0? That is the question. So this is where this location of roots theorem come into the picture. It says, okay, see, even if you can find the interval in which this 0 lies, then also you are really close to finding a 0. It means it is better than nothing, right? You want to find a 0 of a function. So first of all, what you will do, you will want yourself to be in the proximity of the 0. That is, you'll want to find an interval first. First step should be find an interval in which that 0 lies. Second step should be, can we can we compress this interval in the sense that at every step you are getting a smaller and smaller and smaller interval, and this is where this location of root comes into the picture. So we'll see the application of this location of root theorem with this example. So step 1, okay, I'll write like this: since f of x is continuous, it is continuous everywhere, so in particular it is continuous function on 0 comma 1, and f of 0 times f of 1, it will be, f of 0 will be minus 2 and f of 1 will be e minus 2. So minus 2 is a negative number, e minus 2 is a strictly positive number, so hence the product is 0. Hence the product is strictly negative. So location of roots this theorem location of root theorem implies that a 0 of fx, this function fx lie in this interval, right? 0 comma 1. Okay. Now on the real line, we know the real line, and this is our 0 and this is 1. So we know that this root of fx, one root of fx lies in 0 comma 1. Okay. Now can we shorten this interval? Can we cut down the length of this interval? So what do? We check at the midpoint of this. So midpoint of this is half. So what is the value of half? F of half? See, f of half is half root e minus 2. and this is a negative number, this is a negative number. So what does it imply? So on 0 it was negative. Okay, let me use different pen so that it is clearly visible. On 0 it was positive. Oh sorry, on 0 it was negative. On half also it is negative. But on 1 it is positive. So what does it imply? What does it imply? Again, location of root. Location of roots theorem implies that a zero or root, same thing, a 0 or root of fx lie in half to 1. Okay, see, so this is some progress, right? Earlier at the end of step 1 we had this interval 0 to 1, right? 0 to 1. Now what do we have? We have that, okay, root lies in half to 1. So this is at the end of step 1. So this is at the end of step 1. And this is at the end of step 2. So those who have joined late, I will come to those just in a minute. So today, as you know, is the first tutorial session for this numerical analysis course, and so far what we have seen is the definition of sequence and what do we mean by a convergence of a sequence, and continuous function, what do we mean by continuity at a point and on a subset of a real number. Then we are seeing some properties of continuous functions. For example, the primarily being the location of roots theorem. So please, if you have any doubt, unmute yourself and ask. This is a discussion session, so I encourage you to ask doubt. Okay. So Usha and Saurabh, do you have any doubt? Am I audible first of all to you? Saurabh and Usha? Ush. Ush. Okay. Then I'll continue. So you keep on doing this and you will realize the interval gets halved at the end of every step. At the end of every step. And this is precisely the idea of the bisection method, which you already must have learned, I assume. Do you know the bisection method, guys? Have you seen this bisection method? Okay, so I am not going to explain the this bisection method here, but the spirit of bisection method we have discussed. Okay. Now the last theorem that we will need is the Rolle's theorem, which involves the differentiability of a function. Rolle's theorem. Rolle's theorem. So what does it say? The theorem goes by the name of Rolle's. It says, suppose that f on this on some closed and bounded interval is continuous and not only that, and then hello,
Sorry.
and that, no, it's fine, and that the derivative f dash exists at every point of AB, this interval, such that we have equality on the endpoints. F of A is same as f of B is same as 0. Then there exists at least one C in this open interval AB such that f prime C is 0. Okay. Now it has a beautiful geometrical interpretation which I would just explain in a minute if you will allow me. Then we'll go to the questions. If this is our graph and let's say this is my A, okay, let us so if this is our A and this is our endpoint B, now what does it say? You draw a continuous function f which is differentiable, so which means you cannot take sharp turns, and also you have to make sure that at endpoints f gets 0 as the value. So for example, you start like this and then you end like this. I want to draw so see, what you can see here is the following. At this point, let this point be C. At this point, because it is a point of maxima, f prime C is 0, this point, and there is another point because it is a point of minima, so we know at the point of maxima and minima that derivative takes 0 value. Let's say this point be D. So this is the geometrical interpretation. You can get 2 points. Okay, yeah. So is there any doubt up until now? Please ask. Please ask if you have any doubt. Do you have any doubt? I'll wait for a minute, then we'll continue to the questions. So this is called the Rolle's theorem. Okay. Now we see some problems based on what we have learned. So, questions. So, okay, let's start with the limit and continuity question. So, question 1. Let L be a real number. Let capital L be a real number, and let A and B a sequence of real numbers Now, if there is a positive integer, which means a natural number, a positive integer capital N, and a mu is some real number between 0, 1, such that mod an minus L is less than equal to mu of mod an minus 1 minus L mod. This holds for all n greater than equal to n. Now we are given this. Then what can you say about limit? Then show that limit an as n approaches infinity is capital N. So what should be the argument? Can anyone tell? Can anyone tell what will be the argument? Okay, let's start. Proof. what do we do? We can use this inequality again and again in the following way. So we have been given mod an minus L is less than equal to mu an minus 1 minus L. Now what can you say about this mod an minus 1 minus L? Now can we say that this is actually less than equal to mu square mod an minus 2 minus L? Yes? Can we say that? Saurabh? And what about the others? Please participate in the discussion. Am I audible? And what about the next step? In the next step, what you will get? Now, if you apply this inequality on mod an minus 2 minus L, we'll have an minus 3L modulus times mu, and because mu square is already there, it will become mu cube. So if you keep on doing this up until you reach this point mod an minus n, or let us say I want to go to an, then here it will be n minus capital N, and this holds for all n greater than equal to n. Now see, this is a fixed number, right? This is a fixed number because capital N is fixed number. So since mu is between 0 and 1, we must have, what can you say about limit of mu power n? What can you say about this limit if n goes to infinity? What can you say about this? Anyone? Okay, so this limit will be 0. So using sandwich theorem, what does sandwich theorem say? It says, like, because we have proved that mod an minus L, anyway this is going to be 0, greater than 0, and already we have proved that this part is also true. For all n greater than equal to n. Now because the convergence of the sequence does not, I repeat, does not depend on the behavior of the first initially finitely many terms, so it does not matter what happens behind the stage capital N. So this sandwich theorem will say the limit will also follow this inequality. And note that this is independent of n. Okay, so this you can treat it as a constant. This is independent of n. So this limit is actually 0. This limit, so since limit n goes to infinity mu n minus n mod a capital N minus L is 0, we have what do we have? That limit of this is 0. And this is same as saying, and that is, this is same as saying that limit of the sequence an is actually L as n goes to infinity. Okay. So with this we finish our first question. So if you have any doubt, please ask. If you have any doubt, please ask. Do you have any doubt? See, if you don't ask, then how would I know you have any doubt? Okay. So please ask. Otherwise, let's go to the second question. This we have already seen, but okay, we'll discuss. Let f be a continuous function on this interval a comma b. So let this be a continuous function such that the following holds. Then we need to show that, then we have to show that the equation fx equal to 0 has at least one root in the interval a comma b. A comma b. So as you know, we have directly seen this as a consequence of Rolle's theorem, but okay, let's see this again. If for students who came late, now see, given f of a times f of b is 0, then what can you say about the f of a and f of b? So we know that one of them at least has to be negative. Either f of a is strictly negative or f of b is strictly negative. Because if both of them are non-negative, then the product will be non-negative. So either f of a is negative, either this happens, or this happens. In either case, we have that, 0 lies between f of a and f of b. Now since f is a continuous function, on AB, then by location of roots theorem, Oh, earlier I said Rolle's theorem. No, sorry, it is location of roots theorem. By the location of roots theorem, so what does location of roots theorem say? That if you have a 0 between f of a and f of b, then there will be at least one root in the interval a comma b. Then by the location of roots theorem, there is a number c between a comma b such that f of c is 0, and we are done, right? So this problem uses location of roots theorem. So up until now, is everything clear? If you have any doubt in this problem, please ask. If you have any problem, please ask in this question, or for that matter in any other concept. Okay. Question number 3. Let fx be a continuous function on capital A comma capital B, and let x1 up to xn this be a point in, this be n many points in closed AB, and again let g1 g2 up to gn, let these then be non-negative real numbers then we have to show that I going from 1 to n, this sum f of xi gi f of for some xi in a comma b. So is the question clear to each one of you? If not, then please ask. Is the question clear to all of you? Why are you not saying anything? Students, Saurabh and USH, are you there? Saurabh, are you there? Okay. So let us see how should we proceed in this question. This is actually a very interesting problem. Very interesting problem. So proof. So what are we given? We are given that gi is actually non-negative and I is equal to 1, 2 up to n. this is given. Now let us define capital M to be the maximum of these fxi, where the indexing runs over I, and small m to be the minimum of this fxi. So these are finitely many points, right? These are finitely many points, f of x1, f of x2 up to f of xn. So maximum minimum will exist because this is a finitely, this is a set of finitely many points. What about, if this set had been infinite, for example, this xi's are infinitely many points, then also maximum will occur. Why? Because a continuous function on a closed and bounded interval attains its maximum as well as its minimum. Okay, but in this case, the first thing is these are only finitely many points, and hence the maximum as well as the minimum will be attained. So that is the thing. So then what do we have? Then we have m times summation gi, I going from 1 to n. This is less than equal to because each f of, so you consider this sum in the middle, because this is what we have been asked about. See, this sum is same, we are talking about this sum, and we have written here only this. Okay, so its upper bound will be coming from small m, sorry, lower bound will be coming from small m, and upper bound will be coming from capital M, right? So it will be less than equal to capital M gi, not f of xi, gi, I going from 1 to n. Now from here we have two cases. If C summation gi, this sum is 0, then what can you say about each gi? Then we know each gi will be 0, right? Because as gi is already non-negative, so if sum of non-negative number is coming out to be 0, the only possibility is they have to be 0. Then in that case the desired conclusion is trivial, because this side will be 0 and this side also will be 0. Okay, so then summation f of xi gi is 0 and is same as f of x summation gi okay, and this will hold for every x, this will hold for every x in AB. So we just need to choose one. Okay, we need only one, so you can choose any point in case 1. Now case 2 will be, if this is not 0, if this sum is not 0, then what will it be? It can only be strictly positive, right? As gi's are strictly positive. So let this be equation 1. Okay, let this be the equation number 1. So let this be 1. Now when you divide an inequality, so we can divide by summation gi, right? Divide each side in 1 each side in equation 1 by this summation gi. Okay, and see, because this is a positive numbers, this summation gi, so whenever you divide an inequality, whenever you have an inequality and you are dividing both sides by a positive number, then equality will remain same, it won't change. The equality changes when and only when the number that you are dividing with is a negative number. Okay, so see, when you divide, we will have m less than equal to summation f of xi gi, I going from 1 to n. In the division we will have summation gi okay, so this will have now again by the location of roots theorem, what you will have? By the location of roots theorem, see, because this will be equal to some f of beta and this will be equal to some f of alpha, because continuous function attains its maximum or minimum. Okay, let me write. Since f and this alpha and beta, this will belong to your interval for some alpha comma beta. Since a continuous function on the interval AB attains its maximum and minimum. So by the location of roots theorem, we know there exists C, there exists some xi, let's say, okay, let us put some xi, okay, there exists some xi in between alpha comma beta, but this is a subset of a comma b, right? Such that this value in between is attained and will be equal to some f of psi. So hence what do we have? Hence f of psi, hence this summation I going from 1 to n f of xi gi is f of xi times gi. So is this question clear? Again, this was an application of location of roots theorem, right? So is this Solution clear to all of you? If not, then please ask. Okay, let me connect my charger. Just a minute. Yes, so if you have any doubt, please ask. I'm waiting for 10 seconds. Or, I'm waiting. You just please ask if you have any doubt. See, it is going to be a long class. We still have 1 more hour, so you can ask very freely. Earlier, it used to be a 1 hour session, and the reason that it has been extended to 2 hours is because here this is a safe space for all of you to ask doubt without any hesitation, I would rather say. So you should actually utilize this opportunity. Okay, if you have no doubt, then we'll go to another question. So question number 4. Let f be a continuous function from 0, 1. Now this time a very specific range has been given. 0, 1 to 0, 1. Be a continuous function. Prove that fx equal to x has at least one solution. Has at least one solution in the interval 0, 1. Okay. And this result is called the fixed point theorem. It has general structure also, but that will be too advanced for right now. So this is called fixed point theorem. A version of fixed point theorem rather, I would say, not the fixed point theorem. Okay, so do you have any idea how to prove this? This is one interesting problem, right? So do you have any idea how to prove? Okay, I will give you a hint. I will give you one hint. You define this function. Consider the function this function g from like on 0, 1 to r defined by g of x is f of x minus x. So is this a continuous function? Is this a continuous function? The function g, because it is a combination of two continuous function, right? See, f is a continuous function on 0, 1, and this small x, this is also an identity function, right? X goes to x. So this is a combination of, this is a difference of two continuous function on 0, 1, hence it has to be a continuous function. This much we know about the algebra of continuous function. So the function g is continuous on 0, 1. This is point 1. Second thing, you note that g0 is actually f of 0, right? And what is the value of f of 0? It is greater than equal to 0, right? As the range of f, because f of 0, 1 is contained in 0, 1. This you should know. This is where we have used the fact that the range of f lies in closed interval 0, 1. And what about g of 1? G of 1 will be f of 1 minus 1. So clearly it has to be negative, and again from the same reason. Because the range of f, it starts from 0, if at all it may start. I mean, every number in the range of f will be greater than equal to 0 and less than equal to 1. Okay. So see, so what do we have? If g0 is 0, then we are done. If g0 and if g1, so we can assume g0 and g1 are non-zero. Why? Because otherwise f of 0 is 0 or f of 1 is 1, and we are done, right? And we are done. So this we can assume. Now if they are non-zero, then what do we have? That 0. Now, so this will imply we have g0 strictly less than, 0 is less than g0 and less than g of 1, right? Yes, so this we will have. So hence by the location of roots theorem, this we know. Hence again, see, this was again a question of location of roots. So by location of roots theorem, what can we say? There is some c between open 0, 1 such that g of c is 0. That is, what does it mean? F of c is c, and this is precisely what we have to prove. Okay, so if you have any doubt, please ask. Do you have any doubt? Okay, let us go to question number 5. Question number 5. Let f be a C3 function on the interval a comma b if f has 7, if f has 7 distinct zeros in AB, then show that f triple derivative, third derivative of f, the third derivative of f has at least 4 distinct zeros, 4 distinct zeros, and this question, I'll start with one pictorial representation because it has a very beautiful geometric argument. Proof. See, on this interval a comma b, what are we given? This is our a and this is our b, right? Now f is a C3 function. What does a C3 function mean? That it is a 3 times differentiable function and the third derivative is continuous. Okay. So now it has 7 zeros. Let those 7 zeros be, okay, let's say alpha 1, alpha 2, alpha 3, alpha 4, alpha 5, alpha 6, alpha 7. So here these are the zeros. They can be equal to a, this, this yeah, okay. So these are 7 zeros. Just okay, geometric idea. Let me write geometric idea. Now it must be very clear that which theorem you will have to use. You'll have to use the Rolle's theorem, because Rolle's theorem is a theorem which gives you the existence of a zero of a derivative. Okay. So f has 7 zeros here, f has 7 zeros. Now you again apply Rolle's theorem on f dash. So somewhere here you will have 1 0. Let it be beta 1. Somewhere here you will have another 0. Let it be beta 2. Somewhere here you will have beta 3. At least 1 0, right? Beta 4, beta 5 and beta 6. See, there can be more than 1 zeros in alpha 1, alpha 2, in the interval alpha 1 comma alpha 2. Instead of beta 1, there can be many other zeros of f prime. Okay, but at least there will be one. That is for sure. Okay. So these are the zeros. Now see, again if you apply the Rolle's theorem on f prime, what you will have? You will have that between beta 1 and beta 2, you will have another 1 0 of, at least 1 0 of f double dash, then another 0 gamma 2 between beta 2 and beta 3, then gamma 3, and similarly gamma 4, and then similarly gamma 5. Okay. See, all these gamma 1, gamma 2, gamma 3, gamma 4, gamma 5, all 5 of them will be distinct because they are coming from disjoint intervals. Okay. So they will be distinct. Now see, again this is third time differentiable. So you apply one more time. Okay, so between gamma 1 and gamma 2 you will have theta 1 as the 0, then here you will have theta 2, and here you will have theta 3, and then theta 4. So see, you are getting 4 distinct zeros, but the question is, are these the only 4 zeros? And the answer is no. The answer is no, because Rolle's theorem doesn't say that it has exactly 1 0 in that interval. It says it has at least 1 0. Okay, so all these theta 1, theta 2, theta 3, theta 4, all are zeros of f, third derivative of f, and they are distinct as well, but there can be many other zeros. Okay, so is this clear? I mean, the idea is clear. I'll write formally, mathematically I'll write, but is the idea clear? The idea should be clear. And at every step we are using Rolle's theorem. Okay, we are using Rolle's theorem. Okay, so this I'll give you as an exercise to write it down as a proof. Okay, so let us move to the next question. Question number 6. Evaluate an approximate value of the function fx equal to ex at x equal to half. Just a minute, this iPad is where are we? Yes. Okay, is my screen visible? Yes, now is it visible?
It's visible.
Harish, do you have any doubt?
No, sir.
Okay. So this is using Taylor's polynomial of degree 2 that is, we have to evaluate. In the lectures you must have seen this notation t subscript nx. So we have to evaluate t2x about the point a equal to 0 and obtain the remainder R2 of 0.5 in terms of some xi in real number. This is one thing that we have to do, and secondly we have to compute the value of xi, and because It might be difficult to give exact value, so what we are demanding, you just give the approximate value. Compute approximately a possible value of psi. Okay, so is the question clear to all of you? Yes. So we'll use the Taylor's theorem here, obviously, because we have been asked about the Taylor's polynomial, right? So using the Taylor's theorem, we have f of x to be f of 0 f of 0 plus f prime 0 x plus f double prime 0 x square by 2 factorial plus f triple prime 0 x cube by 3 factorial. And because we want our derivative, because we want to compute t to x, so the remainder term will be f third derivative of f evaluated at some point xi times x cube by 3 factorial. And if you compute this, because the function is nice enough, so it will be 1 plus x square by 2 factorial, then plus e xi x3 by 3 factorial. Okay. Why? Because see, fx is e power x. So every derivative of f will be e power x only. And what is the value of exponential function at x equal to 0? It is 1. So you just plug in the values and just check. Okay. So up until now, is it clear what we are trying to do? Saurabh? Okay. So this gives, therefore, t2 of x, this function is actually 1 plus x square by 2, and t3 of x is same as, oh sorry, oh, where is it go? I wrote down. Now just give me a minute, I'm trying to figure out what happened. Yeah, that is there, that is there, that is there. Oh, somehow some questions have been deleted. Why? Okay. Okay, but okay. Oh god. Then I'll have to write again this question. Okay, I'll quickly write, just give me a minute. Evaluate and Just give me a minute. Some technical glitch happened, due to which these questions and the subsequent proceedings have been deleted. So I'm just trying to write so that every question is visible to all of you when we share the PDF. Obtain the remainder term R2 of 0.5 in terms of some unknown xi in R and compute approximately possible value of xi. So already we have seen this is very bad, like we wrote down so much. Anyway, since fx, I'll quickly write what we have done. Since fx is ex, we have uh, Taylor's theorem gives that t2x, what will be t2x? It will be f of 0 plus f prime 0 x plus f dash 0 x square by 2 factorial. Now if you plug in the values as I was discussing, it will be 1 plus x square by 2. This is our Taylor polynomial of degree 2 and remainder term, it will be third derivative at some unknown xi times x cube by 3 factorial, and this will be some xi in R. Okay. Now what do we do now? We have to evaluate Taylor's polynomial at 0.5. Okay. So we put x equal to 0.5 in T of the Taylor's polynomial of degree 2. Please, if you have any doubt, please stop me and ask. Okay.
Okay.
To get an approximate value of f of 0.5, and we know what is this. This is given by f of 0.5. It is considered to be same, approximately equal to this, and this value, what is this, 1 plus 0.5 plus 0.25 by 2. So this, if you compute, then this will be 1.625. Okay. Now let's go to the remainder term. For the remainder term, we get R2 of 0.5 so see this part, you know, because third derivative is e power xi, so we can write it as e power xi x cube by 3 factorial. Harish, please mute your mic. So if you compute this value, then you will get approximately 0.02. I have computed this value 0.020833 times e power xi. Now, to obtain the values of the unknown xi, to obtain the value of the unknown xi, you know what do we have to do? We have to know the exact value of, we have to know the exact value of f of 0.5, and that is not difficult, right? Because we know f and is equal to and is equal to 1.64872. This is correct up to 6 significant digits. Correct up to 6 significant digits. So then what do? We know the remainder term. What is the value of remainder term, right? See, if you subtract f of 0.5 minus t2 of 0.5, we know these two values, and this will be equal to r2 of 0.5. So this will imply 1.64872 minus 1.625 is same as 0.020833 into e power xi. And if you solve this equation, you will get e power xi to be approximately equal to 1.3857821. I am writing up until I have computed 148. Okay. Did my screen freeze? Is that visible to all of you? I don't think so. Okay, let me reconnect. I'll join back. Just I think there's some technical issue. Am I audible?
Yes.
Okay, so we have this value of e power xi. Now if you take logarithm on both sides, taking logarithm on both sides, we get xi to be, I'll write up to 6 significant digit, 0.129780. Okay, so this is the question. So if you have any doubt, please ask. I'll stop for a while. Okay, I'll stop for a while. We can have like 2 minutes break. Okay, so if there are no doubts, then we move to the next question.
Yes, sir.
So question, which question is this? Sixth. Okay, yes. So the question is here with me now. So let just a minute. I need to, this internet is creating problem. So let capital F be a differentiable function. So be a differentiable function and xn be a sequence xn be a sequence defined inductively by be such that, so this is the inductive relation that we have. And like such that, okay, let us write this way, that this limit xn exists and is equal to x. Further assume that f prime x is 0 then show that xn plus 2 minus xn plus 1 is same as little o. Little o means the order o, okay? So little o of xn plus 1 minus xn as n goes to infinity. So this we have to show, and if you are not familiar with the definition of the little o, then please see the lecture series. Meanwhile, in the proof I will also explain. See, by the definition of the sequence, xn, we have xn plus 2 minus xn plus 1 equal f of xn plus 1 minus f of xn. Now if we use Lagrange's mean value theorem, using Lagrange's mean value theorem, we have that there is some xi n between xn plus 1 and xn such that this xn plus 2 minus xn plus 1, which is same as we know f of xn plus 1 minus f of xn. Now this is where the Lagrange's mean value theorem comes into picture. It can be written as f of xi n times xn plus 1 minus xn. So thus we have xn plus 2 minus xn plus 1 upon xn plus 1 minus xn to be same as f dash xi n. Now since we know that since xn goes to x, this is given, right, as n goes to infinity, and this xi n is bit, so you know, like, so this will imply xn plus 1 also should go to x as n goes to infinity. Now see, since xi n lies between xn plus 1 and xn, so we can use the sandwich theorem. So you please use the sandwich theorem. To get that xi n goes to x as n goes to infinity. So let this be equation number 1 and this be equation number 2. So using 1 and 2, we have limit xn plus 2 minus xn plus 1 upon xn plus 1, you know, this limit you consider, okay? So it will be same as limit f prime xi n as n goes to infinity. Now see, f prime is a continuous function. Okay, f prime is given to be a continuous function. So then this limit will be f prime x, which will be 0, and this is what we wanted to prove, right? And this completes the proof. This completes the proof. So the session is almost about to begin. So if you have any doubt, then please ask. Do you have any doubt?
No, sir.
Okay, I will wait. Okay, so let's go to the last, maybe the last question of today, and this is again very easy question. So this is question number 7. Prove or disapprove, prove or disprove, sorry. First part is n plus 1 and this sequence. This has same capital order, capital O, 1 by n square as n goes to infinity. So what do you think? What answer it should be? So pause the video for a while if you want to see. Otherwise I am proving or disproving this, whatever this turns out to be. So most of the time students are confused with this small o and capital O definition. So you please revise the notes carefully to see the definition and learn it properly, as it will help you in the exam. So we will prove it by the limiting argument. So let an to be this sequence, n plus 1 by n square, and bn be 1 by n square. Then you know this an by bn, it will be oh sorry, this is 1 by n, yeah, sorry, this is 1 by n. So this will be 1 plus 1 by n, which goes to 1 as n goes to infinity. So the limit exists. Okay, so therefore an has same order, capital O, as bn. Now let's go do the second part. 1 upon log n and small o of 1 by n as n goes to infinity. So you can use the definition, but here I'll use the limiting argument once again. See, limiting argument is easy to check, but it does not mean that you should not go with the definition. You should know both way, okay? Limiting argument. So if you choose, let an to be the 1 upon logarithm sequence and bn to be your 1 by n, then an by bn will be n times logarithm n, and we know that it goes to infinity as n goes to infinity. So thus Thus 1 upon logarithm is not same as this of 1 by n as n goes to infinity. We can check this with the definition also. It will also be true, okay? So in today's session, what we learned, okay, I think I'll stop here with the questions. Just a minute. So this was a very long session and I hope you learned something out of it. So let us go through what we did once again. In the first half of today's session, what we discussed is the following. We first saw the convergence of a sequence in terms of the epsilon n definition, and using this we define the continuity of a function at a point, and this definition is said to be the epsilon delta definition of the continuity. Then we saw some preliminaries and results. The first one and the very important one being the location of roots theorem. It says if you have an interval closed a comma b, then like if a continuous function on an interval attains positive and negative values, then it will definitely be attaining the zero values. See, why this theorem is useful, again as we have discussed, is because of the fact that it is used to locate the zero. That is why that is why the name, the location of roots. It may not explicitly tell you the root of a function, a zero of the function, but it can help you in exploring in which interval it will lie. It will give you the location, and that is also a lot, right? I mean, this real line has infinite length. So where is the zero? That is a very challenging task. So if you can locate at the very first stage, if you can restrict yourself in an interval, that is also a very great deal of achievement. And this theorem helps you achieve that. Then we saw the location of roots theorem. This theorem says the derivative will have a 0 between any two zeros of a function given the continuity and differentiability hypothesis. We saw the geometric meaning also. Then we move to the question. The questions were basically on the location of roots theorem. Many, almost like the half of the questions were based on the location of roots theorem. Then we saw one question on Taylor's theorem, and after that we have this question on the small o and capital O. And again I want to say that there are n number of students who have confusion for this small o and capital O definition. Please revise them thoroughly. And to prove or disprove these type of questions as is visible on the screen, you can use the definition and the limiting argument, either of them. But at the very same time, you may feel comfortable using the limiting argument. You should not forget that checking via the definition you should also know. Okay. So with this I finish.